This is the second lecture of group actions. So what we have learned in the last lecture, we were discussing about the group, what are the group actions, and the several examples of actions. And after that we defined orbits, orbits and the various examples of orbits under the action of G. And what is the action? I'm giving you a simple, just an idea. G is a group. Okay, just a second. Yeah, so G is a group and S is a non-empty set, and G acts on S. G acts on S. Okay, fine. Suppose when there exists a function f G cross S to S, it satisfies two properties, that is that es is equals to S for every S inside S, and for every G dash inside G, G dash S, this is actually nothing but G of G dash of S, right? So if this two property satisfies, then we say G acts on S, right? So this is the actual definition of group action. So then we have defined the several examples, and after that we defined the actions orbit, right? Orbit of any element S is actually all those G dash S such that G inside G. This is called an orbit of S, and S is an element of the capital S, right? So don't confuse between small s and capital S, and I am denoting the small s as this and the capital S as this, right? There is a distinction between them between them. So anyways, this is not a matter of us. So my point is today, my aim is to prove the orbit stabilizer lemma, and some I will prove in a nice way that involves with equivalence relations. Okay, so now I am going to prove this. This is an example. This is an important lemma. This is called an orbit stabilizer lemma. Did not go to the name for this, and I am defining an equivalence relation. So I have a group. So suppose I have a group. Suppose G is a group, S is a non-empty set. Remember that S should be non-empty set, right? S is just a set. There is nothing special with S. Just can be anything. So anything. So I'm defining a relation, equivalence relation, defining let that. Sorry, this is called, suppose this be a relation, this is be a relation on S, and the relation is defined as follows: that any element S1 is related to S2 if and only if there exists a G inside G such that GS1 equals to S2. Can you quickly verify that this sorry, what happens here? This relation is an equivalence class of relation. Sorry. So this is an equivalence relation. What do we need to prove is, first you have to show this is a reflexive relation, right? So G is a group and S is a relation, and S and sorry, not S, actually I don't know his symbol is called, but this is a relation on S, right? And S1 is that means the related to S2, or you can write it as S1 is related to S2 where R be a relation. That's why I have written. So there should not be any confusion regarding this. And then so the relation is, can you quickly verify that this relation is an equivalence class of relation? So first check that is reflexivity. What is reflexivity? Reflexive, right? So when you call this is reflexive, so reflexive means that if every element should related to itself, right? So S1 should be related to S1. How? For every S1, for every S1 inside S, how to show? You take G to be E, right? Then E S1 by the action of G, this is actually S2, sorry, S1, right? So this relation is an if reflexive. This implies the reflexive, right? Symmetric. What is the symmetry? If S1 is related to S2, then S2 should be related to S1, right? So this is called symmetricity of a equivalence relation. So let S1 is an element, right? S1 is related to S2. So S1 is related to S2. What does it mean? This implies that there exists a G1, sorry, G inside G, just that GS1, which is equals to GS1, yes, GS1, sorry, GS1, this is equals to S2, right? You have to show that S2 is related to us. You have to show that there exists a, so what can we write? This implies that S1 just operate inverse G inverse of S2, right? That implies that G, if G is an element of G, then G inverse is also an element of G, right? So G inverse of S2, which is equals to S1, right? So this implies that S2 is related to S1. So is it clear? So S2 is related to S1, right? So this implies that is symmetric. This is symmetric, right? So the reflexivity, symmetricity has been done and has been taken care of, and we have only left out with whether it is actually going to be an transitive relation or not. How do you check the transitivity of a relation? Transitivity, it actually means that transitive, so transitive, suppose S1 is related to S2, S1 is related to S2, and S2 is related to S1, S2 is related to S3, then you have to show, just to show that S1 is related to S3. How do you show? What do you mean by S1 is related to S2? S1 is related to S2 means that S1 is related to S2. This implies that there exists a G1 inside G, such that G S1 is equals to S2, right? And what is the meaning of S2 is related to S3? This implies that there exists a G2 inside G, such that G of S2 equals to S3, right? So you have to show that there exists, sorry, G1, G2, and here is G2, S2, G1 is 1 equals to S2, and G2 is S2 equals to S3. You just have to show that G3, sorry, there exists a G3 inside G, such that G3 of S1, this is equals to S3, right? How do you show it? So G1 is related to 2. From here you can write, what you can write is, so GS1 equals to S2, this implies that S1 equals to, this implies what you can say, S1 equals to G1 inverse S2, right? And here S2, right? And in case of S2 you can write, sorry, in case of G1 in S1 equals to, so G1 inverse S2, you need to show that is S3. Suppose this is S3, and you need to just verify the S2. You just sorry, you just have from here. So G of S2, which is equals G2 of S2, which is G3. So what is S2? S2 is G1 of S1. So G2 G1 of S1, which is equals to G3, right? Not G3, this is S3. Just wait for a while. This is So from the first inequality, I guess we are having, so g2 of s2, so g1 of s1, so g2, from this g2 of s2 equals to s3, right? And g2, and what is s2? S2 is g1 of s1. This s2 is g1 of s1, s2 is g1 of s1. This is equals to still s3, right? This implies that there exists a g3, which is equals to g2 g1 inside g, such that g3 s1, this is equals to s3, right? So this is the actual, this is the transitivity. So this relation, is an equivalence class of relation, because this is an equivalence class of relation. So this is an equivalence class of relation. So every equivalence class of relation partition the set, right? You know, every equivalence class of relation partition, if you have any set. So this is a set. So this, if you have an equivalence relation, this will partition the set into some disjoint classes, right? It will partition the set into k distinct classes. It will partition the set into k distinct classes. Suppose partition means that there is the disjoint union. So actually this is actually called the S inside S, and class of S, this is actually S. This will give us the entire the set S. S will partition into n. This is actually, the notation is called the disjoint union. That means that, sorry, disjoint the union. Also this implies that this is not an union, but this implies that the intersection is empty, so there is no common element. So the intersection is, so there are disjoint union, right? So there is no intersection of them. This is a class, this is a class, this is a class, this is a class. So every equivalence class of relation partition the set into n distinct classes. So what is the definition of class? We are having the class of any element S. Class of any element S is actually all those S dash inside S, such that S dash is related to S dash is related to S, right? I guess, just one second, my, yes. So S dash is related to S, right? So S dash is related to S, this called, right? So what are the elements here which S dash is related to S? What is the relation here? So this implies that all those S dash inside is such that S dash is related to S, that means G of S dash equals to S. So you can write as S is related to S dash, so G of S equals to S dash, because our relation is this, there exists a G such that G of S. So what is this? Actually S dash is actually GS, such that G inside G. What is this? This is nothing but orbit of S, right? So class of S is nothing but orbit of S. So class of S is nothing but orbit of S. Is not it a class? So there exists a G such that GS on equals to. So all those elements GS such that G inside G1, right? So this is actually the class, the definition of class. Definition of class is actually orbit. So you know that under classes, two classes are either identical or disjoint. So there are some small exercise for you, that two so orbit of S intersection orbit of S1 intersection orbit of S2 is, sorry, not you can write it as something like orbit of S and orbit of Y, and orbit of Y are either identical or disjoint. That means either they both are same or they are distinct, right? because the classes are distinct. That's it. You just have to use the idea of classes, right? This is a small exercise for you. So orbits are either identical or disjoint, right? So GBA group which is acting on a set and partition distinct orbits under the action of G on S. G acts on X, and this under this action, this group, this set is the set is partitioned into some classes, into k distinct classes. In other words, the S is union of orbits, and any two distinct orbits are disjoint. Okay. So now we have another notion, that is stabilizer, which is called stapes. There is another notion for this. This is called stabilizer. We denote it by stapes. Stab of S is actually all those G inside G which fixes X. That means G of S equals to S. Which fixes X. S. So stab of S, that all those elements which is clearly is contained in G, right? In fact, stab of S is contained in G. Okay. In fact, we can show that this is a. In fact, this is not only the subset. Stab of S is a subgroup of G. This you can show. Try to show. This is very easy. You just take two elements from stab of S and just use the definition of two-step subgroup test. This is, if you have clearly, this stab of S is non-empty, right? Because identity is always inside here, will be here, because identity fixes every S, right? So stab of S is actually all those G which fixes X. So E will be fix every S, right? E will fix every S. So identity is always belongs to a stab of S. This is not empty, right? This implies that stab of S is not empty, right? So you just have to take two element G1 comma G2 inside stab of S. You have to show that G1 G2 inverse inside stab of S. That's it. So it will prove that stab of S is a subgroup of C. This is very easy example, so I'm not going to do this. And what we are lefting out with, this is the definition of stabs, right? This is called stabilizer of it. Stabs means stabilizer of it, which stabilizes the element, right? So we have orbit. So what we have till now, we have orbit of S. These are all those the elements, okay? So G dot S such that G inside G, right? And what we have is stab of S, that means stabilizer of S, right? All those G inside G such that which fixes S, right? We have this two. Till now we have these two. So now we are coming to orbit stabilizer lemma. Just this is called orbit stabilizer lemma. Just highlight it. I guess this color will be good. This is called orbit stabilizer lemma. This is very orbit, not this color is not showing, so not this color. I will choose something different, right? Orbit stabilizer, the spelling lemma. What it says actually, this is called orbit stabilizer lemma. What it actually says that orbit stabilizer lemma says that G is a group, H is a set, G acts on S, then the same thing will happen GBA group. Oh, this is also not showing. So GBA group, and S be a non-empty set, which is non-empty set, and G acts 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 on S, then there exists a bijection. Then there exists a bijection. Suppose like it phi from G mod stab S to orbit of S, right? So G be a group and S is a non-empty set. Then G is acting on S, and there exists a bijection phi from G mod stab S to orbit of S. So this is called orbit stabilizer. Let's see the proof of this. Suppose proof, right? So that notice that this may not be a group, because stabilizer of S may not be a normal subgroup, so this may not form a group, but this is a coset, right? So this may not form a group. This quantity may not be a group, right? So we don't bother about don't think about there as a group. They just think as a set, right? So G is a G mod stab S is actually there is a bijection. That means there exists a bijection. G mod stab S to orbit of S. That's it. There is no group here. Just G is a group, and stab S is not necessarily a normal subgroup. So this is called orbit stabilizer lemma. Let's see the proof. For the convenience, let's say stab of S equals to H, and orbit of S equals to H of S, and orbit of S is O of S, right? So what you have, that you have a map from G mod H of S to O of S. You have to show this map is a bijection, right? The map is bijection, that there exists a bijection. So you take any two what are the elements? This is a coset, right? So you can write GH, you take it to GS, because orbit of S, this will be is this map is a well defined map? First of all, the question is this map, whatever the map you have taken, is this an well defined map? This is why this is an element of O of S, because G of S is always a member of G, because action is G cross S to S, right? So you take GS, this will be definitely a member of S, right? So this is a member of OS, and HS will be there. So G of HS equals to GS, right? This is a member of orbit of S. So my point is this map well defined? First question that immediately you should ask, that is phi well defined? Is this map well defined? So for well defined, you have to you have to take two elements, and if they are same, then you have to show the images should be same, right? That's it. So suppose check the well defined. Let G1 comma HS and G2 comma HS is a member of G mod HS, right? So you have to suppose they are same. You have to show the images are actually same. Okay, so let G1 HS is equals G2 of HS, right? What does it mean? Two cosets are same if and only if you know G1 inverse G2 inside HS, right? What is HS? HS means the stabilizer, right? Just I have defined that stabilizer. What is the definition of stabilizer? The definition of stabilizer actually says that all those G inside G which fixes S. So is fixes S, this implies that this element will fix S. S. So G1 inverse G2 of S is equals S, right? That means every which fixes S. So right, H is a small element here. Okay, so what does it mean? That just G1 of S, just pre-multiply by G1 of S, you will get sub G2 of S equals to G1 of S. What does it mean? This is actually phi of G1 of HS, which is equals to phi of G2 of HS, right? So I have taken two elements are same, because why these are same? G2 of S, G2 of S is C, G2 of HS is actually G2 of S, G2 of S is G2 of HS, right? So I have taken two elements are same, and this implies that this means that this map is an well defined map. This means that is well defined, right? So this is a well defined map. You just have to verify whether it is a bijection or not. Is it a bijection or not? Whatever map I have chosen, this is a bijection or not. So for bijection, let's check the one-oneness. One-oneness. Is it 1-1? So suppose two elements I have taken from for one-oneness, it is the reverse of this kind. Actually, this is actually, suppose two elements I have taken from G1, so same I am taking. Suppose I will now I will take that two elements are actually two images are same. I will take, and I will show that two actually elements are same, right? So I will take, suppose G1 HS and G2 of HS is two member of G mod HS, right? And phi of G1 of HS is actually phi of G2 of HS, right? Right. So now you have to show that G1 of and you have to show if the element G1 of HS actually equals to G2 of HS. You have to show that, that's it, right? So what does it mean? It means that G1 of S, which is equals to G2 of S, right? What does it mean? You just do it as, suppose G1 inverse G2, right? So you just multiply by G1 inverse here, so it will be S, it will be identity, and it will be G1 inverse G2 inverse of S, right? What does it mean? That G1 inverse G2 is a member of HS, which is stabilizer of S, right? Because HS is stabilizer of, we have assumed. What does it mean? G1 of HS is actually G2 of HS, right? So I have taken two images are same, I have shown that two elements are same. This means that this map is 1-1. So this may imply that is 1-1, right? So 1-1 has been taken care of. Here only lefting out the ontoness, whether it is going to be onto or not, right? So onto is it onto set for ontoness? Let, okay, still now we have not talk about any the orbit. Okay, so let S be an element of orbit of S, which is actually I have defined O of S, right? I have just, so we need to show that there exists an element inside G mod HS. G mod HS, you have to show there exists an element in G mod Hs such that phi is those element phi of that element is equals to S. What is the best possible choice for that? So you can phi of you get uh, suppose that E of H. What is this? E of S, right? So what is the map is here? Map is G1 of. So E of, just 1 second. Okay. G1 of S. Yeah, this E of S, right? This actually E of S, which is equals to S. So this is E of S, which is equals to S by the action property of action, right? So phi of identity of S. So there exist E H, which is inside G mod Hs, such that phi of EH, which is equals to S. So this implies that phi is onto. So now my point is this is a bijection, right? So this map is a bijection, right? So if this is a bijection, so the cardinality will be same, because the phi is a map from G mod stab S, that means stabilizer of S, to orbit of S, right? So if this is a bijection, since this is a bijection we have shown, then cardinality of G mod stab S is actually orbit of S, right? So it can be this implies that cardinality of G divided by cardinality of stab S is actually cardinality of orbit of S. So this is orbit of S, right? So this implies that cardinality of G, that means the member of G, is actually the orbit of S into stab of S, right? So G is represented, the member of G is actually represented by the elements of orbit and the elements of stabilizer. It's very nice and interesting proof for that. And all the elements of the group, the total number of group can be found by the orbit and the stabilizer of the group, right? So that's it. So this is called the orbit stabilizer lemma. This is called the orbit stabilizer lemma. Okay, so the number of elements of G is actually the number of elements of orbit of an element into just number of elements into the number of elements of stabilizer, right? This is called, right? So that much for today, and we will continue in the next lecture. Thank you.